So next, let's talk about the BFS algorithm run on a matrix. And as you can see, I'm going to be jumping into the code relatively quickly because we actually have even more code than when we were talking about DFS. But the good thing is, at least in my opinion, that this is more simple to understand visually than DFS. If you recall, BFS, at least when we ran it on a tree, was, something like this, where instead of, starting at the root and then going as deep as we can and then going as deep as we can on the other side, what we did is we went layer by layer. We went through the first layer, then we went through the second layer, and then we went through the third layer, etc., etc. And that's the same idea here. We're going to go through the first layer and then the second layer and then the third layer and then the fourth layer and then the fifth layer, etc., etc. Now, what type of question would this algorithm apply to? Well, by far the most common is the shortest path algorithm. Suppose we want to find the length of the shortest path from the top left to the bottom right and then return that. The best way to do that, the most efficient way, is the BFS algorithm. We could also use DFS if we really wanted to, the algorithm that we just talked about. We could use DFS. We could basically check every single possible path that can reach the destination and then find the length of the shortest one of those. But that's a brute force approach. BFS is actually more efficient. The time complexity of this is actually just going to be the size of the grid. Let's say that's n times m, where, this is the number of rows, this is the number of columns. This is what the time complexity is going to be. Whereas DFS was much, much less efficient. It was 4 to the power of n times m. So let's see how we can run this algorithm in terms of code and why it's so efficient. So the setup is going to be taking the dimensions of the grid. In this case, we're just past a grid. Let's say we already know that the starting point is the top left and we're going to the bottom right. We're going to have a visit hash set just like with DFS. So there are some similarities. We're going to have a queue just like for BFS when we ran it on a tree. The queue is basically going to tell us the current level that we're at. So initially, the queue is just going to be initialized with the first node. That's our starting point, and we're also going to add it to the visit hash set. It's already visited, and now from here, we want to see this is basically all the nodes we can reach with a length of 0. So this is, our starting point essentially. Then we're essentially going to loop while the queue is non-empty, and we're going to take a snapshot of the length of the queue. Initially, it's just going to be just a single element, and we're going to pop all 1 elements, just like with a tree. But when we pop, we know we're not getting a node. We're actually adding the coordinates of the position, and when we pop, we're getting the coordinates of the position. Now, we might have found the result. What if we were at the destination? In that case, we would return the length of the path. Initially, like I said, our length is 0. But in this case, we know we haven't reached the result. So one way to code this up, and basically this is going to look complicated. It's a lot of boilerplate, but once you get used to it, it's pretty easy. It's just a pain to type out, in my opinion, because we have a lot of conditionals. We know we can move in 4 directions, just like we did in the DFS approach. And we know there's a bunch of edge cases. We could go out of bounds. We could reach a position that's blocked. We could reach a position we've already visited before. Those are a few edge cases, and we're handling them the exact same way we did with DFS, where if the minimum of the row and the column is less than 0, we're out of bounds. If the row is equal to the number of rows, we're out of bounds that way. If the column is equal to the number of columns, we're out of bounds that way. We might have already visited it before, or it could be the value 1. That means it's blocked. What we would do in that case is continue. That means we would just continue to the next iteration of the loop. We would just skip this coordinate. But you can see it's not as simple as just taking a row and a column. I'm writing it this way basically to eliminate duplicate code. We could have we could basically have this conditional 4 times for all 4 directions. Or we could put this in a helper function. Another way to do it, though, is to take all 4 of the neighbors. When we say neighbors, these are not actually the neighbors necessarily. These are basically the directions. So this would represent the right direction. This would represent the left direction. this would represent below and this would represent above. So when we take these directions and add them to the row and the column, so that's what you can see we're doing for basically all of these. For row, we're adding dr. Dr just stands for difference in row. We're basically saying how much did the row change? How much is the difference of the row? This is 0, and that means the column is changing, right? Basically what I'm saying is by taking these, which represent the difference in row and the difference in column, and adding them to the row and the column, we will basically have all 4 directions enumerated. So this is sort of more complicated than it looks. You can write it out the long way if you'd like, or you can even, put this kind of stuff in a helper function if you would like. But this is another common way that it's done. And this sort of minimizes the amount of code that we have to write. I could also here have declared another variable saying, the new row and the new column, so that we wouldn't have had to write row plus dr, c plus dc out, multiple times. You can see I had to write that out a few times here, but I wanted to make it explicit in this case to show you exactly what we're doing. But feel free to modify this to make it look more simple or match your coding style, however you would like. But now that we kind of covered what this is doing, this is just a bunch of boilerplate to go through all 4 directions using a loop. What are we actually going to do with those 4 directions? Well, of course, we know that the base case, if we go out of bounds, reach the same position twice, or we reach a blocked position, that's when we do nothing, we continue. Otherwise, it means we reached a valid position. By the way, which one of these 4 is a valid position? Only the one to the right over here. So this is the only valid position. What are we going to do with this? We're now going to add it to our queue. We know that's the next layer. This is the only node we can reach with a path length of 1. So we add it to the queue, and we also add it to visit. We don't want to visit this multiple times now. Now, after we've gone through all the neighbors and we popped this position from our queue, now we have this in our queue, and we popped this from our queue, now we have this in our queue. So after that loop, we're also going to increment the length by 1 to indicate that this layer that we have now added to our queue can be reached. All these nodes can be reached with a path length of 1. So now let's continue. And at this point, I'm going to focus mostly on the visuals. We know we can go in 4 directions, down, up, can't go in either of those directions. We can't go left, it's already been visited, but we can go to the right, and that's the only position we can go to. That's the only thing we're going to end up adding to our queue and adding to visit. And of course, this is going to have been popped from the queue. And after that's done, our length is going to be incremented to 2. By the way, when we did pop this guy, we checked, is it the destination? It was not. So we did not return the length, which at the time when we popped this was 1. So if it was the destination, we would have returned 1, which is what we would have wanted to do. So now we get to a bit of a more interesting case. We only have 1 value again in our queue, but we have 2 valid directions we can go to, right and below. And both of those are going to be added to the queue and added to the visit hash set. We wouldn't be able to add this one, of course, because it's already been added to the visit hash set. And then we would increment our length by 1. So our length would now be 3. So our length would now be 3. I'm going to write the length below now since we're kind of running out of space up there. But basically, this is the layer of nodes we can reach with a path length of 3 starting from the top left. And through that process, we know we would have popped this from our queue. So this is now part of our queue. We're going to go to the next layer. So this is where it's going to get a bit interesting because the length of our queue is actually 2 now. So we're going to pop both of these from our queue. It doesn't really matter which one we pop first. Let's just say we popped this guy first. So we pop it from the queue and we get its neighbors. Can't go up, it's already been visited. Can't go left, it's blocked. We can go to the right and we can go below. So what we're going to do is add these to our queue and add them to the visit hash set. Now you're going to see why we add to the visit hash set as soon as we add to the queue, because that's very important. Because next we're going to pop this guy from our queue. So we pop this from the queue and we see, can we go up? Nope. Can we go to the left? Nope. Can't go to the right. And we can't even go below. This was open, but we added it to the visit hash set. So now we know it's already been added to the queue. So we're not going to add it to the queue again. This is very important. This is why the algorithm runs an n times m complexity, because we know for sure we're never going to add the same position to the queue twice. We're never going to visit the same position twice. And we still know that these are all of the cells we can reach with a path length of 4. So this is going layer by layer. That's very important. So now we have 2 positions in our queue. So we're going to execute this loop again twice. For 2 iterations, we're going to pop, let's say, this guy first. We can't go below, can't go to the left, can't go right, and can't go up. So we pop it, but we don't end up adding anything to our queue. It's just going to execute the continue statement. So at this point, our queue only has this guy. So we pop this from our queue, and then we add its neighbors. Can't go up, can't go right. We can go below, and we can go to the left. So these are now going to be added to our queue. What's the length to reach these? Well, previously it was 4, so let's add 1 and get 5. We can reach both of these with a length of 5. That's the shortest path to reach both of them. Now, we don't actually know what is the shortest path. We're not keeping track of that. It would probably be this or this, but that's not important. We just care about the length in this case. And at this point, we're almost done. We have 2 positions in our queue. Pop this guy. Can't go up, it's blocked. Can't go to the right, it's visited. Can't go below, it's blocked. We can go to the left and add this to our queue and to our visit hash set. And then we pop the last one in this layer. Can't go left, can't go below, can't go up. We can only go to the right. And at this point, we've gotten to the destination. But you can see this is where we look for the destination. After we pop from our queue is when we check, is this the destination? We don't check if it's the destination when we're adding to the queue. I mean, we could have done it this way. We would have to rewrite it a little bit because we're only incrementing the length after we've updated the entire queue. But let's just run this very quickly. So we finished this layer. So now our green layer here takes a length of 6 to reach. Now finishing up, let's say we pop this guy first. We'd pop it and we can't go up, can't go left, can't go right. We just add this guy to our queue and then we pop this one. So when we pop it, we check, is it the result that we're looking for? It is. And by the way, at this point, our length would still be 6. So we would return that and that would be the result. So I color coded it a bit to indicate to you the length of each of these. So to actually run that, you could see BFS would just be past the grid and then the function itself would take care of the rest. And then we could print the result. In this case, it would be 6. The path would look something like this. But that's the main idea. As you can see with this approach, we're never going to visit the same position twice. We're never going to add the same position to the queue twice. Worst case, we'd visit the entire grid. So in that case, the time complexity would be the dimensions of the grid, which is n times m. The space complexity would be the same because that's the max size that our visit hash set or our queue could end up being. So this would be the memory complexity and also the time complexity. So in my opinion, this is a bit more easy to understand in terms of like the visuals. Code-wise, there's a lot of boilerplate though, as you can see. So it can kind of be a pain to write out, but once you get used to it, it's just a matter of writing out all the, edge cases and getting them right. But it can definitely take a while to get good at it. I'd recommend taking a look at some of the problems in the practice section under the graph topic, because BFS is definitely a common algorithm that comes up a lot.